Welcome to the NonSequitur Show. Continual watching beyond this point may result in terminal face palming and a complete loss of wokeness. You have been warned.
Welcome to the NonSequitur Show, and I got to tell you guys, this particular episode took me back a ways trying to prepare for this. For those who don't know, I actually started back in computers way back in the day when I don't think people even called them computers back then. I mean, I was back in the day of a Z80, TRS-80, the K-Pro, CPM, Focal, Fortran, and I was looking over Dr. Miller's here presentation, and I was just like, holy crap, I've forgotten everything about computers. So hopefully you guys, along with me, will kind of learn stuff here. So I have Dr. Timothy Miller here, and he actually was a dude that actually helped to, well, I don't know, debug. I want to say develop Minecraft, but help debug Minecraft. Something along those lines. You'll explain it after I introduce you. Because I still don't fully understand it, because I'm not good at Minecraft. It took me like 3 days to figure out red blocks and tiles and all that stuff. But anyways, I know that you had done some debugging on Minecraft, and you are a CPU expert, a actual engineer. Yes, he is a real engineer with a capital E that actually does engineering stuff. But anyways, Timothy Miller, welcome. Dr. Timothy Miller.
Thank you.
How are you, my friend?
Thank you for having me on the show. I'm going to go ahead and put these on now that I have remembered to do it, so we don't get any echo.
Yeah, headphones definitely do cut back on the echo. Yeah, absolutely. Yeah. So real quick before we even get into your presentation, because your presentation is extensive, and I doubt we're going to be able to get into all of it. So tell the people the story again of this whole Minecraft thing, because I'm really kind of interested in how that came about.
Okay, well, I kind of got into Minecraft. I got kids, and I'm kind of interested in the kind of some of the technical aspects of the game and things like that. So I ran into some weird bugs that were breaking some of the technical machines that I built in the game, and they were really annoying. And a friend of mine had gotten into modding of the game. So he had a way to decompile the game from binary back to source code, and which some people might be familiar with. It's called MCP. It's a Minecraft, the mod coders pack, something like that. Mm-hmm. Anyway, and so I used this to decompile the game, and basically instrumented some of the code to try to figure out what was causing this bug. And there was actually fixed a couple of bugs, and they'd been in the game for like 5 years or something at that point. And the developers had tried over and over and over again to fix them. And they were not successful, and I eventually was. I don't know how much detail you want me to go into. There's actually
were these terminal bugs, or were these like play style bugs?
Okay, so there's a device in the game called a hopper. Okay, so basically if you drop items in it, or you have a block with an inventory over it, then you can suck items into the hopper and into some other block with an inventory. And if you make you can connect two hoppers together and use some other components, and you can make a timer. So I needed a timer that would control the rate at which so this machine I had built was operating. And what would happen is if you would like leave the area where this machine was, it would unload the data in memory that that stored the machine, okay, because you went to a different location in the world. And in the process of unloading and reloading the chunks, it would sort of corrupt the state of the hoppers. And what would happen is you'd end up with extra items. So I would want, say, 42 items to move from one hopper to the other and then back, okay? So that I could, and the items take 7 game ticks to move one item. So I can, decide I want this amount of time to elapse before the timer sends a signal to something. And, but what happened is it would get extra items in the hoppers, just randomly.
Which benefited the player.
Well, you see, it can benefit the player if you want to duplicate something valuable like diamonds in the game, right? But if you want a fixed number of items in the hoppers so that you get an exact timing, and then you are playing the game, and then because the game loads and unloads data, the number of items in the hoppers gets changed, then it's going to mess things up. So it could be advantageous or it could be deleterious depending on what you're going for. In this case, it was deleterious, right? And so so basically there were 2 different bugs. One of them was a thread race condition. You could have a chunk that was being unloaded, and while it was in the process of being saved to disk, something else would request that chunk get reloaded, and you would end up loading a stale version of the chunk into memory. So like an old version, older than the one that's being saved. So that was the second one I fixed. And the first one had to do with if the hopper was going to transfer an item on the same tick that it was unloaded and reloaded, then you would end up with 2 copies of each hopper in memory. And so 2 hoppers would send an item, the same item at the same time, to a different hopper, and you could duplicate items that way. So I figured these out, and some of the more some famous technical players. I don't know if any of your viewers will have heard of people like Nembon and Il Mango and Methods, and people from the SciCraft server found out about the fact that I had posted fixes to these bugs and started talking to me. And like, I think it was 2019, there was a Minecraft conference in Tennessee, I believe. And these guys from Germany came, and they did a little tour of the northeastern US. So they went from JFK through some places to the conference in Kentucky, and then they went through Toronto and things like that. And they came and visited me. So I've gone hiking with a YouTuber who has over 700,000 subscribers.
Yeah, no, Minecraft is still one of the most popular games on YouTube, I understand. And, I played a little bit. My daughter happens to like the game. It's nothing that I find too fascinating. I mean, sure, it's fun for a little while, and I do like making roller coasters. And I remember I made this one roller coaster with the red tiling and made all the switches work, because it's all based on logic, stuff like that. So it wasn't too complicated to learn. But I remember I made this one roller coaster. My daughter was like, did you make that? I'm like, yeah. She's like, holy cow. I'm like, well, it wasn't too terribly difficult. But but I remember other games. Before we do your presentation, to give you a little bit about my history in the computer things, a long time ago in the late 80s, early 90s, somewhere in that ballpark, there were ways to get into games where you can have what was called a soft ice program that would decompile it into the assembly language. And by using that and other means, you can go in and find offset in hexadecimal locations and pretty much change, for example, how much gold you want in the game. There was a game called Eye of the Beholder, which was a dungeon crawl type game, where I would go in, I would have reams of paper, just reams of freaking computer paper, circle, things that are changed, and I would, push things on the stack and change the accumulator and change the registers and see what kind of fix, what did what. And then after a while, I realized, hey, this was the memory location that had how much gold you had. So if I wanted, certain gold, I put FF or something for the maximum, whatever. And then I did it for the weapons. I was able to actually find all the objects, like, well, not all of them, but most of them. If I wanted this sword, it was this hex location with this number. And that back in the day was something that I was considered, being what would be a true Cracker, because also, you know, you use the same techniques to avoid passwords and things of that nature. But it took years. I mean, not years, but it took months to do some of this stuff. It really did. It took me 4 months to really figure out Eye of the Beholder. But now people just say, "Oh, I'm a hacker, I'm a cracker," and they just download a patch that somebody else did all the work, you know.
Yeah.
Anyways, okay, so let's get into this computer architecture. I actually found this fascinating because, again, I started, you know, I don't know how you're old you are, but I think the first computer
48.
Yeah, okay, so I'm a few years older. So I mean, I started again probably with the 8088 series, and maybe with CPM on the K-Pro series and things of that nature. But that was about the first chip that I kind of remember talking about was the 8088, 8086, 8087 coprocessor. So this for people like our age, this would be like completely fascinating. They should probably remember this stuff because this was the front runner for the computer systems you have now. This kind of stuff. So, what do you got for us, Tim?
Well, okay, so I made a bunch of slides, but you know, let's make this interactive, because like just think of them as visual aids for whatever comes up, right? So so where would you like to go with this? Would you like me to just sort of start into some of like, would you like me to start talking about some history, which I'm not that much of an expert on, or would you like me to start talking about like the general design of like how CPUs work and how they do their job? Because that's actually, I taught that for
that's probably what I would be
years.
more interested in. But we can ask the audience though. Like the audience is bringing up their computers like the Atari 800 XL. I had my dad used to sell the Atari 800 XL and the Atari 400. he worked for a company called Video Concepts in Brea, and I remember as a kid, like, you know, I remember. Do you remember the Atari 400 had a flat membrane? And I don't know who developed that idea because you can't really type on it. But I remember programming small things on those things that would do weird things with lines and geometric shapes. And I was like, oh, man, this is like the future right here in our hands. But I think, you know, if you want to touch on the history, that's great. But I think the architecture is probably what most people would probably have more of an interest in. But we'll see what they say. But yeah, what do you got?
Okay. So, well, yeah. So, you know, feel free to ask, like, so this is some background on me. I don't know how much you want to know, kind of gone over a little bit. So, you know, I sort of brainstormed on like topics that I'd kind of like that I could cover. But there are certain things that are like milestones in the history of computer architecture that I think that are interesting to me that I think we can share. Like, you know, I won't necessarily remember exactly when they occurred, but like, you know, there's certain advancements that occurred that were big improvements in the way CPUs worked in history. So we can kind of come back to this slide, you know, for inspiration on things to discuss. And so I went and looked up some things about some like early mechanical computers. So I kind of figured out how like the difference engine worked. We can go into that if you want. But why don't we start at like a basic level of how digital computers work right now? Okay, so basically, a CPU is made up of millions and millions of little tiny switches, and a switches started out as like relays and mechanical components, and then there were vacuum tubes back in the early 20th century. And then we went from vacuum tubes to discrete transistors. I got a picture of so up on the lower left, you got photos of discrete transistors here.
Mm-hmm.
And
these are NPN transistors.
Yeah, these are TTL transistors.
TTLs, yeah.
TTL logic will be made of these. And then, you know, so a lot of computers up through into the 60s were made out of discrete transistors. So there'd be these huge circuit boards of, you know, you'd have other components like capacitors and diodes and things like that. But for the most part, you'd have switches made up of transistors. And then later, they started putting multiple transistors onto a chip. So you had small scale integration. I'm not sure that's what they really called it, but you could have of several transistors on a chip like this one that would give you, several logic gates. And then you could wire those together on a breadboard, like which you can see, or a wire wrap board, like which you can see on the right there. So basically,
these transistors are just essentially solid state versions of what would you originally call valves, which were tubes, right? So
exactly,
you had the original tubes, the first valve, which would be a diode. Then you had a transistor type theory, so it would be a triode. Then we had pentatodes, and as they increased in complexity of the valves, they just integrated that into some kind of small solid state circuit that would perform the exact same electronic functions, right?
Yes, exactly. Right. And so basically what you want is something that can switch. So actually, I should have, just now occurred to me that I really should have shown an example of a CMOS logic gate, because this is like ancient technology that we see here.
I started with TTL.
This is,
Everybody thinks
this is TTL. Really ancient, right? So here in this, I don't know if you can see my mouse pointer.
Yeah, that's really, I mean, people on the outside might have to make their screen like full size for this. But
yeah, let's see, can I, oops. Yeah, I might be able to, what I could do is take this thing and make it a little dynamic, and make that bigger.
Yeah, that's how I remember biasing a transistor. I mean, I don't know if you know, but I was a Radio Shack store manager for 6 years off and on.
All right. Oh, okay.
So, I also had a ham radio license when I was 13, KB6 HSZ. So I had to familiarize myself with transistor biasing and AM, radio communications, FM radio communications. So this takes me back. This really takes me back.
So you can, well, now see, so biasing is an important thing that you want to do with an analog circuit, where you want to make an amplifier. Okay, so where you want a linear amplifier, what you want to do is put the transistor in a state where it's like kind of halfway in the middle of its linear range, because a transistor doesn't have fully linear response, but there is a linear range, and so you can make a voltage divider on the base to the transistor, and get it sort of right, where the 0 point is in the middle of the linear range. And then you have some kind of signal like from a tuner coming in that oscillates around it, and you can amplify that signal. But with digital circuits, what you want is extremely high gain amplifiers. You want these things to switch as fast as possible. Okay. And so now, I mean, digital circuits are fundamentally analog circuits. They're just really high speed, high gain amplifier analog circuits. And actually my graduate school research, my PhD research, involved dealing with some of the effects of the analog behavior of the transistors in these devices that you aren't normally exposed to, but they can be unreliable. So an example of a way it could be unreliable is, let's say your CPU is running along and it's doing a relatively light amount of work. It can be worse with a GPU. GPU is a huge sea of simple CPUs. And let's say you've got a relatively light graphics load, and then all of a sudden you blast it with a maximum amount of work. Like, you run a program that puts your CPU to 100% or your GPU to 100%. What'll happen is the circuit will start switching more, and that will draw more current. And if your voltage regulator can't keep up, then that will cause your supply voltage to dip, at least momentarily, until the voltage regulator catches up. And what happens then is, because your supply voltage is lower, your switching speed is slower. And then if you've got, you'll have there's going to be a lot of terminology that you may have to have me back up on. Okay.
I had to repair power supplies. So I'm familiar with voltage regulation.
Well, yeah, but so here I'm talking about the switching regulator right next to a CPU, because you have your big power supply that gives you like 5 and 12 volts, but then you got a voltage regulator that's supplying like 1 volt to the CPU, but it's got to be a really stable 1 volt. And if you start drawing a lot of current, it can cause a dip in that. Dip in the supply voltage causes switching speeds in the transistors to slow down, which means that the amount of time that it takes signals to propagate through logic slows down, and let's say you've got a circuit that performs a multiplication. Okay, so you got 32 bits of A and 32 bits of B wired into this big circuit, and those bits are coming from. Are you familiar with flip-flops?
Flip-flop,
like the little
yeah,
bit storage cells.
Flip-flop.
Right? So
like I said, Radio Shack had flip-flops.
Yeah,
We had
right.
4888. What is it?
Right.
What were the operational amplifiers?
I don't remember, but yes,
4444s or something. I know. I remember
Right.
555s.
Right. So in a digital circuit, we'll call like a set of these things, we'll call them a pipeline register or just a register, depending on what you're doing with it. Okay. So let's say we've got a register that has A and B, these two 32-bit numbers, big giant logic circuit that performs multiplication, and then they connect to another register C, right? Now, there's a clock signal that's controlling when data is registered in A and B and appears on the output and can start propagating through the circuit. And then one clock period later, that data better have arrived on the inputs of C, because you're going to clock that register and send it on to the next thing. And if the circuit slows down because the voltage dips, then the computation will not complete in time, and you'll register some garbage. Okay. And there's actually a term for this where the voltage dips too low and causes the circuit to slow down. It's called a voltage emergency, which is a term that makes some sense. And this is one of the ways in which a CPU can be unreliable. So this is, there are other ways like that it can be unreliable, like memory cells can get hit by cosmic rays. So you can have something called an SEU, a single event upset, or a soft error is another term for this.
Even if you had one gate that was in the wrong binary state due to whatever reason, whether it lost, like you say, even a cosmic ray can cause a flip of a binary state. You again, there's some redundancy, I assume, in a lot of the stuff, but for the most part, you're going to have some kind of errors creep in. Matter of fact, it's funny because the very first power supply I remember building, I had to be around somewhere between 11 and 12, I guess, right? And I thought I was a badass, right? I had just got back from Kansas. I raided my grandfather's old electronics shop that he had sealed up, and I'm just like, I want this. I had a flyback transformers, and I had what was called a selenium rectifier, and so I had built this power supply for like a CB, not understanding at the time the difference between a regulated and unregulated. So when I keyed down, it just went to hell. The first one actually wired the primary back to the secondary was even worse, and my parents weren't happy. But so you're saying that on the voltage from the main power supply unit, that has to be a very low voltage, but it has to be regulated in a way that voltage remains absolutely constant. So you have you have that synchronicity of events happening in order to get the output when it goes to the each cycle, right?
Yep. So so anyway, so we'll go back to the digital world, and we'll
Awesome.
talk about just the kind of logic gates, the kind of circuits that we want to produce here. Okay, so here we've got a primitive technology. We have a NAND gate. Now, so a NAND gate is gonna let's see, I think I have a truth table for an AND gate here. Okay, so right here, and so here, if it has an output of 1 or true or high voltage, whatever you want to call it, only if both of the inputs are 1. Okay, and so a NAND gate is just inverts the output. Okay, so here what we have is normally if there's no signal into these, or they're low, then these transistors are both off. Okay, and so what's going to happen is there's this resistor that's connected to the supply voltage, and so there's nothing pulling it low, then the voltage level on this output signal is going to be high. Okay, so
and this is where you would actually use a digital logic probe to check your states.
Right, exactly. So now if you provided a high signal, so basically a potential difference between ground and A, for instance, that's equal to the supply voltage, then it's going to switch on this transistor, and this will become conducting. Now, by itself, that's not enough. You have to turn both of them on. So you'd have to also turn on B. What that will do is we'll make both of these transistors conducting. And since these transistors together will have a lower resistance than this pull-up resistor, then this will get pulled low.
Oh, sorry, I just hit my mic.
Okay.
Yeah, and there's obviously a lot of background electronics involved in this stuff. I mean, look, I took BWE, and I understand Kirchhoff's voltage laws and Kirchhoff's current distribution and all that stuff. I'm not expecting the audience to get like a really full in-depth thing on electrical theory, but this is explaining in a way that I think that everybody can understand. So this is great because even people have never had any electronics. It's kind of intuitive the way he's explaining it, rather than having to go in and dive into the math, because the math sucks, by the way, for this stuff. It really sucks. But intuitively speaking, it just makes sense. You're just drawing away the current to ground rather than having to go to the gate. So it's just taking two inputs. If the inputs are both not high, you're not going to get a high value out. That's it.
So now one of the drawbacks of this, now see, back in the day, it really didn't matter. You had so few transistors on a chip that they wouldn't really draw a tremendous amount of power no matter what. But still, it's unfortunate that one of the problems with this thing is that there's always current flowing through this resistor. So it's this logic gate is always drawing power. So I should have included stuff on CMOS, but I went ahead and Googled it. So can you see this?
Yes.
So here we have a CMOS inverter. Now this is a MOSFET, and I probably shouldn't. Metal oxide. I'm not going to. I'm not going to go into the huge amount of background as to the difference between these transistors, between the TTL and the metal oxide transistors. But what we have here, but this is complementary metal oxide semiconductor. What's complementary about it is that instead of having a pull-up resistor and pull-down transistors, okay, the pull-ups and pull-downs are all transistors. So this circuit will only conduct when it is switching, and when it's not switching, it doesn't conduct, so it doesn't use any power.
Yeah, so it's more efficient, but at the same time, CMOS is much more sensitive to things in TTL. I mean, static electricity, especially.
That is true. That's some of the analog stuff that I'm not, as much of as familiar with, but because I don't really know exactly why they're so much more sensitive. It could be that there's like a gate breakdown. There's an insulator between.
Yeah, I think it's on the boundary
conduction channel.
Yeah, I think there's a boundary there that has I remember the static electricity will break down the conduction point between like the channel, the actual channel, because you have your I remember the terminology is very similar for CMOS as just TTL, but they're called different things like the gate, the drain, things of that nature, right?
Yeah.
Yeah.
Yeah,
You're making me go back a lot of years on this.
There's a drain, the source, and the gate here, and the gate isn't actually electrically connected. And so, if you want, I can go into how the functional theory of a MOSFET. But basically, with this inverter here, let's say A is pulled high, so it's connected to the supply voltage. What that's going to do is switch off this PMOS transistor and switch on this NMOS transistor. And that will create a conduction path to ground. So the input's high and the output is low. And if the input is low, then that switches off this transistor and switches this one on and creates a conduction path from supply.
And PNN just means positive, negative. So it's been doped to have either a higher positive charge or a negative charge. So when they say PNP, it means a positive region, negative region, positive region. So it just means that it's been doped by some kind of doping agent, whether it be gallium or whatever they use.
Like phosphorus and boron, typically, commonly. So I mean, it's not really positively charged. What it is that the crystal lattice has an excess of electrons or a deficit of electrons in the conduction
there you
band.
Go. That's a better way to explain it. You're right.
So
that's why he's a PhD and I'm not, but he's right.
Well, I haven't studied electrical engineering since the 90s. I had to know a bunch of this stuff, and like I did have to kind of know it when I was doing like digital circuit design. There's another way that I'm not really famous for it, but I ought to be. So there's a chip that back in late 90s, early 2000s, FAA contracted Raytheon to replace all these radar screens in the air traffic control towers, and Raytheon contracted TechSource that I worked for and to supply them with graphics cards to drive these giant. Back in the day, these monitors were 2K by 2K resolution, which is no big deal today, but back then those monitors cost $35,000. Okay, so TechSource supplied the graphics card, and I designed the graphics chip on that card. So when you fly in the United States and several other countries, there are terminals that the air traffic controllers are using to monitor planes in flight, and I designed the graphics chip that is in those machines.
Nice.
So
I kind of lost my thing here. I'm setting this up again. I don't know what happened. So go ahead and continue. Oh, I lost the presentation for some reason. It's on my end, so I'll fix it here. I'll figure it out. Just give me a second here. You go ahead and continue. Like I said, I will.
Well, I have visuals.
Oh, yeah, visuals. Gotcha. Why is this not show? Oh! I know why it's not. Okay, I think I got this. Give me a second here. One second. There we go. Got it back. Yay.
All right.
Technical error.
So
see what happens when computers have errors? Yeah, so
what we want to do with these switches is we want to compute. So you see how we turn transistors into logic gates, and now I want to talk about how we turn logic gates into things that can do math. Okay, so here we have some basic logic gates. We have the inverter. I talked about that. It just changes the 0 to 1 and 1 to 0. If an AND gate, that's only true when both inputs are true. You have an OR gate that's only false when both inputs are false. And another important one is the exclusive OR that only has a true output when only one of the inputs is true. If both of the inputs are false or both inputs are true, then the output is false. Okay. So, what I've done here is I've shown a single bit binary adder. Okay. So what it's going to do is going to take so when you do arithmetic, like in decimal, so I want to add, 555 plus 555. Okay. Then in the first column, I'm going to add the 2 5s and I get a 0 and I carry the 1. Okay. And then I get, an 11 there and carry the 1, and I get an 11 and carry the 1. Okay. So the same thing happens in binary, where if you add 2 zeros, you get a 0. If you add 2 1, you get, if you a 1 and a 0, you get a 1. But if you add 2 1s, what you need is a 0 with a carry of 1. Mm-hmm. Okay. So this is base 2 arithmetic. Mm-hmm. And so in this circuit, we're going to take 2 bits A and B. It's associative, right? It's addition. And what we want to do is compute their sum and the carry. And you also get a carry in, so you can cascade a set of these full adders, so you can add add 2 numbers that are whatever width you want in bits. Okay. Just by connecting from the least significant bit to the most significant bit, they connect the carry out of one adder to the carry in of the next. Okay. So we got 2 1s here on A and B. Then this exclusive OR is going to give us a 0. Okay. Because 1 plus 1 is 0, plus 2. And
it depends if you ask a flat earther or not, to be honest.
Right.
So math is completely different from what I'm used to.
So we get a 1, we get a 0 coming out here, but we also have this AND gate down here that sees that both of these are 1s, and it's going to give us a 1. Okay. And so we get a carry out of 1. All right. So then we could have a carry in of 1 as well. So let's say all 3 of these were 1. Okay. Then you'd, the 1 exclusive OR 1 will give you a 0 here. Exclusive OR this other 1 on the carry in will then give you a 1 as the sum, because 1 plus 1 plus 1 is 3, right? Mm-hmm. So we need a 1 plus a carry of 1, and it will notice that, at least 2 of these inputs is a 1, so that the value is 2 or 3. So it's at least 2. So the carry out will be a 1. And so like I say, you can cascade these together and you can add numbers as large as you want. Then you can cascade large numbers of adders together, like you could do, like the way you do multiplication. You can cascade adders together and make a multiplier. And so you can build circuits of whatever you need to do whatever kind of math that needs to be done, because that's what a computer does. It does math really fast.
I got a couple questions. I one for myself and then I one for the audience, but I'm going to ask the audience question first. Somebody wants to know, why are CPUs not made double the size to give more room for transistors? I get there's a cut up. I don't know what that means. I get there is a cut up point due to distance covered by electrical signals. I think they're asking, like, why don't they just make these things bigger? Obviously, I think I'm going to guess. I would obviously say I think it's a heat dissipation thing, and also on your silicon layer, you're limited by a boundary because of quantum mechanical effects. I think it's like 8 microns, 6 microns, whatever it is. I think right now, what are they at? Like 8 to 9 micron level. But I think that those, when you have a bigger chips like that, you have heat dissipation and quantum mechanical effects you have to take into account. But what does the expert say?
Okay, so the quantum effects are at the individual transistor level, and we could talk about that, but that's a separate concern. Okay, so I'll list some of the reasons that we don't want the die to be too big. All right, so when you manufacture chips, we have a big wafer, thin round wafer silicon, and we have a bunch of duplicate copies of the chip, okay, on the wafer, and then we cut them out, okay, and one of there is a signal propagation thing where as the chip gets bigger, then it takes longer for signals to propagate across the chip. But you can deal with that. There are ways to deal with that, like you can add extra pipeline stages in your CPU, or that's not such a big deal. There is a heat dissipation issue. The larger it is, the more power it's going to consume to do, the same unit of work per unit of area. Okay, but actually the biggest reason, I believe, is yield. That the yield loss is a function of the 4th power of area or something like that. So the bigger the die, the higher the probability that you're going to have a manufacturing defect, and that means you have to throw away more of the chips. So you want to minimize the size of the chip. And so like Apple just came out with the M1 Ultra, which is basically 2 M1 systems on chip, like stitched together. And why do they do that? Because you can get higher yield than if you tried to put them all on one big chip.
Yeah. Do you remember?
And yield is
Oh, I'm sorry. No, go ahead.
Well, yield is really important. It's a huge cost factor. When a chip first comes out, especially when it's a new technology node where the transistors are shrunk and you have to go through all these growing pains on transitioning to a new technology. There's high yield loss, and it's very expensive because it can cost you like $1 million to tape out a CPU, and you have to produce them in the millions in order to be able to sell them economically. So we want to maximize the yield.
Yeah. Do you remember way back when they had 6 Sigma methodologies, and that was to and so that was to reduce the amount of defect in a substantial amount of product. Because 6 Sigma is extremely small as far as error, and so even with these chips, I can imagine if you have such a mass production and you have obviously going to have error rates, and the bigger the chip, the bigger the error in the manufacturing, the higher cost wastage you're going to have, and so it makes obviously the other chips more expensive as well. So it's something along those lines.
Yes.
Okay.
Yeah. Now modern CPUs, like half the die area is dedicated to cache, and it's just a large array of memory, and so you can afford to lose some of that. Like they'll over provision the cache memory.
That's your L1 and L2.
Yeah, like the L3 cache, for instance, will be heavily over provisioned so that you can lose a fair amount of it, like have to, laser it out, like disconnect it with a laser. So they'll run tests on it and determine which portions of it are bad and basically dewire it from the circuit. And that's a good way to keep the yield up. But when your logic is bad, then if you have one way to keep the yield up, for instance, is if you had designed your CPU, and we're getting way ahead of the discussion here. But if you got a chip with 8 CPUs on it, if 4 of them are bad, well, what you do is you use your laser to cut the connections to those CPUs and sell it as a 4 CPU chip. And it, so you don't waste the silicon, and you sell it at a discount, and it's still more profitable than throwing it away. Sure,
that makes sense. And the question I was going to ask real quick was just not spend too much time on it, but when they're designing these chips, do they start off how do they? Obviously you could build it up very simply. You can start with a truth table and say, look, this is what I'm going for. These are the actual chips I need to make this happen. I need an OR gate, I need an AND gate, and you can base it simply off truth tables for a very small thing like this. But when you start dealing with millions and millions of transistors on these wafers, how the hell do these engineers keep that in their head of what the hell is going on? It's ridiculous. It's ridiculous. It's like magic.
It's not. So for some of the most there are going to be some very limited parts of the design that are going to be hand optimized. But for the most part, these things are designed in a hardware description language. It's a high level language. It looks kind of like C or Pascal, that where you describe, if you want an adder or a multiplier, you use a plus sign or an asterisk, and the software, instead of a compiler, you have a synthesizer that takes your high level language and converts it into logic gates, and will figure out how to where the transistors are going to go on the chip and how to wire them up, which is an NP hard problem.
Oh yeah, that's a topic for another time. Absolutely.
All automated tools. Yeah. So automated tools are the answer.
Yeah, no, that makes sense.
If the humans are not doing all of this work.
We're not going to answer this next question because I'm going to postpone it to another show, because I think it should be another show. But somebody had asked about quantum computers, but quantum computing is next level. I mean, I'm sure you could probably speak on it, but it would be way too much to even touch on here, because the way quantum computers work is it's next level.
Yeah.
So
yeah, it's a radically different approach.
All right, what we got?
So, okay. Let's see. All right. Okay. So where do I want to go next? I'm going to okay. So let's, you could, like I say, you can direct me here, but let's talk about, the basic compute cycle. So now we're moving at a higher level. We're not talking about circuits anymore. We're not talking about how it is physically implementing these kinds of things, but like, I've got a part of the CPU that's got a bunch of complex logic whose job is to get it in instructions. Okay, so what's an instruction? So let's talk about maybe what instructions are. What would be a good one? Okay, this is the NMOS 6502. Here's a table of instructions. They were byte opcodes. So here's the upper 4 bits and lower 4 bits, and I want to tell the CPU to add something. So somewhere in here is some add instructions. Here we go. And basically, if I have the hexadecimal value 65 in memory, it's going to tell the CPU to add 2 numbers.
So that's add to the compiler, and then add with carry. Add with the 0 point carry.
Yeah.
A float is that a 0 carryover, right?
Yeah, from no. So I believe that this one is going to take 2 numbers. One of them is in memory. The other one's in the accumulator. And it's going to add them together plus whatever's in the carry flag.
Okay.
So you would, if you wanted to add 2 numbers without a carry, there's an instruction that would clear the carry flag. This is a very primitive CPU. This CPU was designed by hand back in the 70s. Okay. So this is back in the day when we didn't have hardware description languages. Okay. So anyway, I feel the need to try to make sure that it's understood what an instruction is. It's like, so where should I go with that? I got a slide on, where do I have the slide on this?
And by the way, this is the code. This is very, I mean, not exactly like that, because the versions I used was a different code. But I mean, when I was decompiling some of the stuff, and it would go into, you remember the old days where you could put obviously debug and it would show you the assembly language. These are the instructions you would go in and have to literally change in hexadecimal in order to say, okay, I don't want it to jump to this location. I don't want it to add 2. I want it to add 1. I don't want it to do this. I want it to do that. And you would have to go in, and without screwing up the entire program, because if you weren't careful, it's super easy to crash that stuff.
Yep. So here I'm kind of jumping around a little bit. So hopefully people don't get too confused. But there's can give you a definition here. So when we're talking about hardware and the physical design of the CPU, okay, we call that the microarchitecture. Like that's the implementation of the CPU. But there's a language that the CPU understands, that's the instruction set, and we call that the instruction set architecture. So think of the instruction. So I don't know if anybody has heard of Toki Pona. It's a
No.
constructed language. It's a conlang, okay, that has 127 words. Okay, it's actually quite expressive. Okay, somebody made up this language, and when they made up this language, they had certain ideas in mind about what the semantics of this language were going to be like. Okay, so when you're designing a CPU, you're going to do something similar. You're going to say, all right, well, I need to be able to do these mathematical operations, add and bitwise and subtract and multiply and you know all these kinds of things, and I need to be able to jump around from place to place, like what you would do with an if test. So you're going to decide what the language is that this family of CPUs is going to understand when they're running programs. Okay, and that's the instruction set architecture. And then now you can then say, well, let's take x86. All right, 32-bit CPU architecture from Intel, and there's families of CPUs that execute this instruction set. And I'm pointing at my monitor, and nobody can see me doing that, which is just silly.
But
anyway,
I do that all the time. Actually, I really do. It's like I have my camera off, and I gesticulate a lot. And so even with the camera off, I find myself like doing all those hand motions. And I'm like, nobody can even see me. What the hell am I doing? But it's just a habit.
Mm-hmm. So, so here are some, instruction set architectures like x86 and the 64-bit version, 32-bit ARM instruction set, like in older cell phones, 64-bit ARM instruction set. And then we have CPUs that are implemented to understand those instruction sets, like the 8386 and the Intel Core i7, ARM Cortex A53, the AWS Graviton 2, which I've had to work with myself at work. And so basically we have a language that the CPU understands that defines the things that it's capable of doing. So I've got an accumulator and I want to add some data from memory to it. Okay, now I have a sum. What can I do with that? Well, what I could do is I could compare that to another number. And if it's greater than that other number, I can go jump to a different place of the program. And otherwise I can continue executing as I was going. Okay. So I have, for instance, a program here whose job is to multiply two numbers in 6502 assembly language. And so what we're going to do is we're going to load a 0 into the accumulator and an 8 into this index register. And what we want to do is we're going to shift there's one of the numbers, num2, that we want to multiply is in memory. And we're going to shift it right. What that's going to do is it's going to take the lowest bit and it's going to move it into the carry flag. And so now I can decide if the carry is clear, then I can branch from here to this other place in the program.
All right, so it's going to be stepping through this, right? It's going to be stepping through this.
Yeah.
And
it's going to step through the multiplier and add or not add the multiplicand.
And this is what you were saying earlier about having to have each clock cycle have to do an operation. Right. And so,
right. So in this case, it's not necessarily a clock cycle. So an instruction could take multiple clock cycles.
Sure.
But so what I'm describing here is not the digital circuitry, but the language that the CPU is the machine language of, the CPU.
Right. So loads the accumulator, loads the data X register, DX register.
Yep.
Okay.
And then, so now if the carry is not clear, okay, that means the low bit of num2, which is this multiplier here, is set. Okay, then what I want to do is add num1 to the accumulator. Okay, so the accumulator starts out as 0, and if the multiplier bit is 1, then I'm going to take this multiplicand and I'm going to add it to the accumulator, to A. Okay, so if the carry is clear, I'm going to skip all that. But if the carry is set, I'm going to I need to make sure that I don't add an extra 1. Okay, so I'm going to clear the carry and I'm going to add num1, which is this multiplicand, to the accumulator. Okay, so whenever there's a 1 in the multiplier, I'm going to add this, and whenever there's a 0, I'm not going to add it. Okay, so either way, I end up here where I'm going to rotate the accumulator to the right. Okay, what that basically is going to do is take the lowest bit and pop it up on the left, and effectively it's going to change the order of magnitude of the number, so that if I add something to it, I'm adding 2 times that number, right? Because what I need to do is I need to take this multiplicand and basically shift it left by 1 in order to decide whether or not I'm going to add it based on this bit.
Sure.
I need to shift it left again to decide when I decide whether or not I'm going to add it based on this bit. Okay, so I'm going to do this by rotating the accumulator right, so that I can just take the multiplicand and just add it straight up. Okay, so so I'm going to rotate the accumulator. I'm not sure why there's an extra result register, but anyway, now I'm going to decrement this X counter because there's 8 bits in the multiplier. So I'm going to count down, and if the counter has not reached 0, I'm not done. So I'm going to jump back to here and add and check the next bit of the multiplier to decide whether or not to add the multiplicand.
So, all right, so DE is decrement, not EX register, right?
Yeah, this is the decrement the X register.
So you decrement the X register, and then it branches if not equal.
Which is, and not equal means branch if non-zero.
If non-zero, so then it goes back. So it keeps on going until it decreases to 0.
Right. Once it gets to 0, then we're done. And so we're going to store the accumulator in memory. Actually, so what's happening here is the result. It's going to produce a 16-bit result, and I'd have to think about a little.
Yeah,
bit
I'm so used to like 8-bit, and then obviously it went to 16-bit, and then it went to 32-bit, and then it went to 64-bit, which is, again, each time you're dealing with more registers, and also you're dealing with more bits as far as your high and low. For example, if there's 8 bits in num2, then you have 4 high, 4 low, right? And then you have 16, we have 8 high, 8 low. Then you have 64, it has 32 high and 32 low. It gets really complicated really fast, but it's able to do far more processes when you have more registers you can work with and more bits that you have larger architecture, right?
Yeah. So like if you want to do a 64-bit add on a 32-bit CPU, it's going to take twice as many instructions.
Yeah.
If you want to do a 64-bit multiply on a 32-bit architecture, it's going to take 4 times as many instructions. So that's just one example. There's also faster data movement. You can pull more data in and out of the CPU registers faster. So
like if my friend Tal says, assembly was basically like any other coding language, just very shorthand. It's very, very low level. It's very, very compactified.
So the 6502 had basically 3 more or less general purpose registers, whereas a modern CPU will have like 16 or 32 or more. So that there's a whole bunch of I think I've got a slide in here somewhere that might mention that kind of stuff. So let's see, where do I want to go? All right, so let's say we got this instruction. I want to add 2 numbers, and so I've got registers. So let's talk about architectural registers. There is data storage in memory, in main memory, but there's also data storage in a very small fixed set of storage registers inside the CPU. I'm not talking about cache memory, because cache memory its whole job is to look like main memory, just be faster most of the time. I'm talking about a fixed set of numbers that can be stored in the CPU that the compiler or the programmer manages directly. And so what you want to, if you want to add 2 numbers then you'll pull the numbers that you want from memory into those registers and then tell it to add them. And then you got a result in a register, and then you can tell it to store that result in memory or whatever it is you want to do. Okay. And so now this turns out to be some random add instruction that I picked from our 32-bit ARM architecture. Because what this instruction is, it's just a number in memory that the CPU's logic knows how to interpret
as an instruction.
So, as an instruction, right? So what I've shown here is I've got a slide where I guess I don't have that. Okay, all right. So I'm gonna talk about a really basic compute cycle. Okay, what does a CPU do? So this kind of looks like a pipeline, which we'll get into pipelining later, but this isn't meant to be a pipeline. This is just meant to be the steps that a CPU goes through. So really early CPUs, first thing they would do is they would fetch the instruction. Okay. Second thing they would do is decode the instruction and figure out what it means. Okay. The next thing they would do is look up the inputs, the source operands, the instruction. Okay. So we access memory, pull in the instruction from memory, send it to some other logic that figures out what it means. Then now that we know what it means, we know what the source operands are, so we can go and maybe access memory to get those, okay, and bring them into the CPU. And then we're going to execute. So in this case, the thing we want to do is add. So we're going to add those numbers. Okay, now we have a result, and then we're going to store that result somewhere, register or memory or whatever. And so you can think at a really basic level, what the CPU does for every instruction is it fetches it, decodes it, looks up the source operands, performs the math that you wanted on those operands, and then stores the result somewhere over and over and over again. So any questions about that?
Yeah. And how many instructions can most modern computers do at once?
Well,
it's in gigaflops or something,
talking,
like huge amount.
Well, yeah, we're
compared to what it was in the 70s.
Okay, so for a 4 gigahertz CPU, I'd say, north of 10 billion instructions per second.
Incredible. I mean, think about this. I mean, like when you and I grew up, I mean, we were looking at things like, oh, I got a 1 meg chip. I'm styling. I got 1 megabyte in my memory, and then you had Gates going, oh, we're never going to need more than 640 conventional, memory. I remember, and I mean, I remember back in the days where you had to use extended memory and you had conventional memory, extended memory, you had to use memory mappers, and you're like, oh my God, I got 2 meg, I got 4 meg, and now it's like people are like, oh, I only got 64 gig on my machine. I don't have enough of memory. I'm like, what the hell are you running? I'm like, what the hell are you running? I need that much memory.
Well, now, yeah, I've got 32 gigs of RAM in this computer that I'm using right now, and it barely keeps up with me.
I don't. What do you run that requires that much memory at one time? Do you have like 1,000 million tabs?
Yeah, I have that, and I could be running Minecraft at the same time.
Minecraft doesn't require that much memory. I mean, I play some high-end games, and I mean, I'll get about 86% of memory use. I think this has 16 meg or whatever it is. Maybe it's 8, but I mean, what do they say? Unused RAM is just wasted. But I mean, still, I look. I'm not pulling a Bill Gates where say, look, we're never going to need more than 640K. But I think a lot of people do overestimate how much memory they probably do use for most stuff they use. I mean, 32 meg for a computer is a lot of meg. Like 2 gig. I'm sorry, 32 gig. But yeah,
well, my work laptop only has 16, and I'm kind of a power user, and I was worried about that. But it's not a problem because I don't have a million tabs open on that one. Just my personal one where I open a tab. Because some flat earther wants to argue with me about something, so I have to look up a reference, and then
the Earth is still round, from what I understand, right? And you're not running AutoCAD.
And then I forget to close the tab,
Yeah, no, I get it. I have a lot of tabs open too. That's pretty much my biggest draw is Chrome tabs, because I have a lot of things. What I do is I even have open windows. Like, okay, I have like one window that just has like some philosophy stuff I want to look back into. Then I have another window that has just like some other stuff I want to look into. And then if it crashes, I can go in and just go in my history and go, okay, I want to reopen all these tabs, which is convenient. But they don't really have a great tab manager. I wish someone would develop a program for that. Hint, guys out there, write a program that better at managing tabs and all this stuff, because Chrome sucks. But anyways, so
I like how the mobile browsers will unload them, but they're there and selectable but they'll free the memory, whereas the desktop browsers.
Yeah, Opera is worse for that. When Opera especially came out, I remember Opera had huge memory leakage, and it even if you closed a tab, it still didn't release that memory, and so the leakage was incredible. And I would be getting like, I'd have nothing running, and I'd be like having like close to 100% memory usage. I'm like, what? It's all leakage from Opera. I mean, I think they fixed most of it, but when that first came out, that was a huge problem.
Yeah.
Oh, look at this. Oh, look at that.
So
that's actually that one you had before.
What?
The one before that one you can't read. That one. There you go. There you go. That's.
I could try to go over this. I mean, I'm not really familiar with the PDP one, but I mean, that's how
to figure. That's the first one something used on a mini computer that had punch tape.
Yeah.
We wrote in a language called Focal, and there were 3K punch tapes. Yeah.
Yeah. So let's see if we can figure this out, because I didn't really spend a lot of time. So it had 4K of 4096 18-bit words. Okay. So if you want to access memory, then there's a memory buffer register. Okay. So if you have a memory address register and you want to load or store from memory, okay, you get that address is going to be connected to the memory, and then you're going to get data out, or you're going to be writing data to the memory. Okay. So you need a register to hold that so that you can do math on it. Okay. And then you have another register, which is an accumulator. So what you normally do is, like, I want to add a bunch of numbers. I'm going to load a value from memory, add it to the accumulator, load another value from the memory, add it to the accumulator, and on and on and on. Right. And so then I've got my final result in the accumulator, and then I can move it into the memory buffer and then store it in memory. That's the kind of approach that people will take. Right. You have another register for doing IO, so you can talk to your tapes and your punch cards. So you get instructions out of memory, right? So the control logic is basically going to say, okay, hey, memory, give me an instruction. Let's put it in there. Okay. Now the instruction is going to tell the control logic what it wants to be done. So that's going to do something like, direct how these registers are going to be connected to the arithmetic logic circuits, okay, that tell it what to compute, and then the result will be put back into the accumulator. You also have a program counter that's just an address of the next instruction that you're executing, and it's going to use that to look up the instruction memory. So one of the things about modern computers, the von Neumann architecture, is that the data and code are stored in the same memory space. Some of these earlier computers, like the ENIAC, wasn't really a general purpose computer. You'd literally have these big giant cards that you would pull out and have these wires that you'd hook up that would indicate how, like, different circuits would feed the output of one circuit into the input of another, and you would wire all these things up, and it would take days to program one program to do something like compute a missile trajectory or whatever. So they didn't really have an instruction set. What they had was a wiring diagram that you could manipulate. Whereas with a von Neumann or even Harvard architecture, just all that does is split the program and data into separate memories, but that's not that important. Anyway, the point is that now, instead of the program being specified by wires, they're specified by numbers that control switches that effectively, at least an abstract way, do the same thing as what those wired cards do, but in a completely dynamic, programmable way.
Gotcha.
So let's see. Here's a block diagram for the 6502. So 6502 was a CPU in the Apple II, the Commodore 64, all the Commodore, PET and so forth, and the Atari 8-bit computers, 800XL and all that. And if you want, I can try to dig through this diagram.
It wouldn't be legible anyways. So
yeah.
But yeah, I remember the 6502, and I remember on the Apple, and then I had a VIC 20, had a Commodore 64, had a TI 994A. Oh my God, old school.
All right, so we went through this. So we were talking about 8-bit computers, okay? And there was a point when so basically, as time went on, manufacturers were able to get transistors smaller and smaller, which meant that you could fit more of them onto a chip. And the more of them that you could fit onto a chip, the more you could do. Okay. And so the first single chip CPU was actually a 4-bit architecture, and it's in the spreadsheet that I'm going to probably go over at some point. Okay. And then they were able to go from 4 bits to 8. And then, the late 70s or something, well, by that point, the process technology, the manufacturing had progressed to a point where, okay, well, now we can do 16-bit numbers. Isn't that great? And then, so it's really constraining. Like it makes it difficult to program if all you've got is 8-bit numbers. So there's a huge programmer convenience, among other things, and to have larger word sizes. But an even bigger deal is address sizes. Like, how much memory can you address at once? If you only have a 16-bit address, you can only address 64 kilobytes. And the Commodore 128 was able to address twice as much by doing something called memory banking, where you were controlling the upper 64K, little 8K slices of it could be mapped into the lower portion of memory. Okay, it's really inconvenient. So when we got to 32-bit architectures, people were like, "Yay, we can finally have up to 4 gigabytes."
4 gigs of RAM.
Yeah, 4 gigs of RAM, right?
Mm-hmm.
But eventually that got to be too constraining. All right, and there was now whatever 2 to the 64 is. Some huge number is the memory limit.
The theoretical, the memory limit. Yeah, because I remember before on the oldest, I worked with a lot of motherboards. Matter of fact, one of the first jobs I ever got when I got out of the Navy wasn't very long, was actually building computers, literally putting them together. I mean, it was just a little shop down here, and you get the case, you get the power supply, you put them all together, put the motherboard in, and they were they were 2 meg, and then they had 2 gig, and then they were 4 gig. Something like that. But I mean, that was literally the highest the board could even use was 4 gig. I mean, so I think it was in the first ones were 2 gig, if I'm not mistaken.
Yep. So now I don't know how much you can see of this, but
I can read most of it, I guess.
The Motorola 68000 was kind of a big deal because the Atari ST series and the Atari and the Commodore Amiga were using this processor, and the Apple Macintosh. Okay. And this was a 32-bit processor. Now, so I mean, it had a 16-bit external interface, but the registers internally were 32 bits, and that was kind of a big deal. And it was also a big deal that it was a flat address space. So the x86 processors, they did this weird thing called segmented addressing, where they'd have these 64K pages, but then the next segment would overlap it. And so so you could have 2 to the 16 pages of 2 to the 16 bytes, but because they overlapped, you could only get 1 megabyte of address space. It was, some nutball thing that people had to deal with back then. And it was a huge big deal when 386 came out, when the Motorola 68000 came out, where we had a flat 32-bit address space. Like there was no segmentation, none of this weird addressing. It was just, there's memory and you can address, So, one of the weird things I remember about the 68000 is we're still back in the day when die area was at a premium. And so one of the weird things they did is they had, I believe it was 16 general purpose registers that were 32 bits. But to save space, they made the registers dynamic. So I don't know if you know the difference between static RAM and dynamic RAM. You probably do. Yeah. But static RAM, you power the thing.
Same with dynamic static IP.
Well, kind of. Yeah. Well,
it's similar.
So with the static RAM, you power it on, you store data, and it just stays there. With dynamic RAM, you have to periodically refresh it. And so they used dynamic RAM cells of some kind for the registers to save space. But that meant that there was so normally a CPU has a maximum clock rate. If you try to clock it faster, then we talked about propagation delay between registers before. If you need a certain amount of time for the computation to happen, and if you try to clock it faster, then the answers don't arrive at the registers in time, right? So a CPU will have a maximum clock rate. But the 68,000 had a minimum clock rate because if you clocked it too slowly, the registers wouldn't hold their contents. Because
it had to be refreshed, and if not, then you lose the data, right?
Mm-hmm. Yeah. Okay, now how illegible is this?
Pretty small. So, that's pretty small.
Yeah. Here, let's see.
Getting better.
Let's see what the audience thinks. One of the problems that I'm going to have is panning.
So those So the first one, it looks like 10 micron.
Here, I'll make it bigger. Let's go to 200. Okay.
Blow it up. There you go. That's
Is this
better.
good?
Yeah, that's good.
Okay,
that's good.
All right. So I kind of made a timeline here of the sort of progression of CPUs. I got a lot of this. There's this document that. Where is it? This Agner guy did a bunch of reverse engineering. And now he mostly reverse engineered Intel and AMD processors, which is why this is so Intel centric. Mm-hmm. But this kind of shows the general trends of CPU development. And so I kind of want to come and go with this. But there's like certain milestones that occurred. So we have these early days of 4 and 8-bit processors, and the transistors are 10 microns. It just means that basically the size of the transistor is 10 microns across. And these things were clocked at less than a megahertz. Okay. And all of these things were simple in order CPUs. You'd fetch one instruction, you'd decode it, do the steps that I talked about before. And in these days, the CPUs were slower than the memory. It's weird. Today, the CPUs are so much faster than memory, you need huge caches on chip just so that they can run efficiently. But back then, the RAM was faster. So you would just fetch the instruction. It would take a clock cycle. Mm-hmm. Spend multiple cycles decoding it and doing all the other work. And every time you wanted to access memory, it would take one clock cycle. One of the things that's going on that we see is a progression on transistor size shrinking. And it was until about 2001 that most of the advancement in clock rate and reduction in power consumption of CPUs was in device physics. So it was like the manufacturing technology. They were able to shrink the transistors by about square root of 2 factor, like every year or something like that. Or like the area of a transistor would be reduced by a factor of 2. And the length would be reduced by square root of 2, something like that. All right. So let me try not to be too confusing because what's happening here is because of my disorganized slides, we're moving into pipelining, and I'm trying to figure out how to get into that. So what I want to talk about here is is how CPUs were made. One of the ways the CPUs were made faster. Okay. And the idea is that these older CPUs would do one thing at a time. They fetch and then decode and then execute and then write back. Okay. Or however they divided it up. But when we move into like the 80s, we now finally have enough die area that we can start doing interesting things to improve the performance by overlapping the steps of different instructions. Okay. So here we've got a laundry analogy. that I stole from my lecture notes at university. Okay. So we're going to do laundry. We've got to wash, dry, fold, and then put the clothes away. And each one takes 30 minutes. So if I've got 4 loads of laundry to do, then I got to do each of these 4 steps. And then I got to do the 4 steps again and the 4 steps again. And each one takes 30 minutes. So this is going to take 8 hours for 4 loads.
Mm-hmm.
Okay. So the older CPUs were basically working like that. So if you wanted, one instruction could take 4, 8, however many clock cycles it needed to, depending on how many things in memory it needed to access. Okay. Pipelining was an advancement in CPU architecture where we're overlapping the steps in executing an instruction. So here in the laundry analogy, we're going to wash load A. Okay, now when load A is done, we're going to move the laundry into the dryer. Meanwhile, we can put load B into the washer. And when that step is done, then I can start folding A, drying B, and washing C. Okay, so now these 4 loads are going to take 3.5 hours instead of 8. And if I had an infinite number of loads, then it would take 30 minutes per load, asymptotically.
Mm-hmm.
So this was a major step in the advancement of CPU architectures. And so we had these early processors like in the 80s, like the ARM1 was a RISC processor that Acorn designed that went into the BBC Micro, that is the ancestor of all the ARM architecture CPUs that we find in all of these mobile devices today. The Intel 8386 had a 3-stage pipeline. I don't know exactly what the stages were, but they were probably something like fetch, decode, and execute, something like that.
So it's fetching something, it's decode, and it fetches, it decodes, and once decoding, it's fetching again, something else, decoding something else. So they're overlapping.
Exactly. Yep, exactly.
Mm-hmm.
So, I forgot about these. So here we have a pipeline. Is this legible?
No.
I can. Okay, let me make that bigger.
Yeah, I originally was going to do this a different way, where I had a lot more clearer. That's why I had it in the center of the layout. But we had to change it up at the very end. So I apologize, or else I would have made this a completely different thing for this presentation. But yeah, that's much more legible.
Okay, yeah, it's kind of like the resolution isn't even very good. Now, this is the pipeline of a MIPS processor, another early RISC processor.
Multi-instruction and here, something or other? What it was?
Well, so MIPS means, okay, no, I don't know what MIPS meant in that case. So normally MIPS means millions of instructions per second. But MIPS is the name of a company, and it probably means something different.
Oh, really? Interesting.
Yeah. The MIPS processor was used in this, I believe, in the Silicon Graphics workstations, if that rings a bell. So, and they had a 5-stage pipeline. And so memory, oddly, despite being off chip and bigger, is being represented by this little box. Mm-hmm. But basically, we have an instruction pointer that is, keeping track of where in the program we are, and that instruction pointer is being given to the memory to look up an instruction. Okay, now these green things are pipeline registers. So a signal is going to be sent at every clock pulse. Okay, so the clock signal goes up and down and up and down. And every time you get a rising edge, whatever's on the input of the register is going to just atomically appear on the output. And so you can think of it as everything that's here, whatever's coming into this register is going to shift to the output, and so it can start doing the computations in this pipeline stage. And whatever was here is going to shift over to here, so it can do the execution and so on. Mm-hmm. Okay, so we got an instruction. And so you could think of the program counter as a pipeline register, kind of. And we're gonna look up the instruction, and it's going to be in this register. And then we're going to, now the way the MIPS instructions were, the decode was almost completely trivial. Like it had a fixed 32-bit word, and the register numbers in the instruction were in fixed fields. So you could, instead of having to do a bunch of complex decoding, like you have to do on Intel processors, you could just literally wire bits from the instruction into the circuitry. So, so we have a register file. The register file contained 32 32-bit numbers. Okay, so we take some field from the instruction that's like source 1, and that's wired into a register number input to the register file, and then source 2 is wired into another register number input, and this is a little static memory, and it's looking up 2 different registers in there, 2 different of these 32-bit numbers, and those are coming on the output. Okay, and you could also have an immediate field in the instruction, which is like if I want to add 1 to something, I can encode that 1 in the instruction. Okay, so that could be another field in the instruction. So this basically is decoding the instruction and looking up the input operands to whatever it is that you're going to do. Okay, so then the next stage is the arithmetic or the execute, and so if you want to add or do a bitwise AND or whatever, the bits in the instruction would instruct the ALU what the operation was that you're going to perform, and this also doubled as an address calculator for memory access. So if you wanted to read or write memory, we have to remember to talk about the difference between RISC and CISC architectures, but this is a RISC architecture, also known as a load store architecture, where you can't do math directly on memory. If you want, like, you never can, but with a CISC architecture like x86, like an Intel processor, you can have operands that are in memory encoded in the instruction so that the CPU will implicitly go and fetch that data from memory, do the math, and then send the data back out to memory. A load store architecture doesn't do that. It simplifies the instruction set. So you have to have explicitly separate load, math, and store instructions. Okay. Mm-hmm. So if we want to do load or store, we can use this in an add mode to calculate an address. And so then the next stage is memory. So that's going to look up if you want to load or store, or it's going to read or write memory. And then when this is done, if you just did math, then it's just going to forward it. It's not going to access memory. It's just going to send it on to this pipeline register. And this pipeline register is connected back to the register file to write a result. So if I want to add 2 numbers, then in the decode stage, I'm going to look up A and B, whatever it is that I want to add. Then in this stage, in the second stage, I'm going to add them. The next stage, I'm going to just pass it through. And then in the last stage, it's going to write the result back to some other register in the register file. So this is like your little tiny, extremely fast internal memory. Okay. And so this being pipelined, while one instruction is being fetched, the previous one is being decoded. The one before that is being executed. The one before that is in this stage. And the one before that is currently being written back to the register file. Okay. So, oops.
Yeah, it definitely seems to increase efficiency. Obviously increases, I would assume, your power as well and needs, but much more efficient.
Yeah. So, let's see, what else do I want to talk about here? Okay. So, okay. So, trying to remember what I was trying to get across here. Oh, okay. All right. So there's another milestone that I want to get to here. And that has to do with out of order execution. So let's go through these. Okay. So the 386 through the Pentium were in order processors. Okay. So they although they were pipelined and could overlap the execution of neighboring instructions, they would only execute the instructions in the original program order. So one of the drawbacks of this is, let's say you've got a memory instruction and memory is slow. So we're getting to a point here in this era, like in the mid 90s, when the speed of the CPU has outstripped the speed of the path to memory. Mm-hmm. Okay. So this starts to make caching become important, which we're going to have to get to. And so here we start to have enough space on the chips, right? So here, this processor, whichever one it is, 386, didn't have any cache because back in this era, memory was as fast as the processor, give or take. Okay. But when we get to the 486, now memory is slower, and we need to start holding on to the most recently used bits of memory, chunks of memory on the CPU. If we don't do that, it makes a huge difference. Okay. So we start to add caches to the CPU to hold on to the most recently used data.
And they're designed into the chip itself, but they're not that huge, but they are hard in the chip itself. The L1 cache.
Yeah. So back in these days, we only had one, only had a small. If you want to call it L1, you can call it that, but it's the only one. Yeah. And so basically, caches are becoming important because the CPU speed is outpacing the RAM speed. Another interesting thing that happens around this era is that we start going superscalar. Okay, so scalars in math are individual numbers, and you have vectors, right? In CPU, superscalar just means you're doing more than one scalar operation at the same time. So the Pentium was the first Intel processor, not the first CPU to do it, but the first Intel processor to be able to support the ability to fetch and issue more than one instruction on a clock cycle. So there was a big performance boost from the 486 to the Pentium, not just because the clock rate increased. So there's like a 3x increase in clock speed from the 486 to the Pentium, but the performance increase was much more than 3x.
Is this because the Pentium had a dual core or something?
No,
because
one CPU.
What allowed to do it?
Yeah. Because so the fetch logic in the CPU was designed to be able to fetch 2 instructions,
even though it's single core.
Yes.
So it's
just 2 adjacent instructions.
I don't know why I can't. I've never been able to wrap my head around how you have a single core being able to fetch 2 instructions.
Well, all it's doing is pulling them out of memory, right? So we're not talking about. I mean, we can execute them simultaneously, okay, but as long as there's no dependency between them, okay. So if you have 2 add instructions that have nothing to do with each other, one's output is not the input to the other, okay, then in theory you could execute them simultaneously. Or a better example would be a multiply instruction and an add instruction, because they're going to use completely different circuits. So why not try to use them simultaneously?
Yeah, I know. I get that. I'm used to having like a step-by-step, like when I learned BASIC, back in the day when they actually had line numbers, right? So you had line 10, 20. So each one was a sequential thing. So it would be like, did line 10, then line 20, and line 30. You couldn't execute line 10 and line 20 at the same time, but using this type of architecture, you can actually do 2 instructions at one time, is what you're saying.
Right. So basically the fetch logic was, so x86 instructions are kind of complicated, but the logic isn't trivial. But like with the ARM processor, when they started going superscalar with these RISC processors, every instruction is exactly 32 bits. So it's trivial. I'm just going to look up 64 bits now. No big deal, right? And so I can grab those 2 numbers into the processor, and I can resolve any dependencies. If there is a dependency, then I'll do one and then the other. Okay. But if there isn't a dependency between them, then I can fetch them simultaneously. I can decode them simultaneously. If they're going to different kinds of execution units, I can issue them simultaneously. Okay. And so this allows me to execute twice as many instructions at once, as long as they're independent. So there's something called a feature, a typical feature of code that people write and that compilers produce is called instruction level parallelism, where there is a degree of independence between instructions that are nearby. Okay. So I wonder if there's an example of that in this in here. Like see this LDA and LDX. They could be done simultaneously. They're operating on completely different registers, right? Or this rotate A and rotate some spot in memory. No big deal. They're completely independent. Now this decrement X, which affects the 0 flag, is not independent of this. So you'd have to execute this one and then this one. Okay. But there's enough examples in here of instructions that could be executed simultaneously. Like all three of these, in fact, could in theory be executed simultaneously because there's no dependencies between them. So basically I wish I could skip through that. This is a slide I stole off some lecture notes.
Yeah. Gotcha.
Okay. So basically, yeah, I'm not sure how to like make it easier to understand. You have a logic circuitry that's looking at memory. Okay, so it can pull in some bytes from memory and is looking at that and trying to figure out what it means, right? It's going to decode the instruction. Okay. Well, you can design that to look at more memory at once, just more bytes. And you can design it to interpret the meaning of more than one instruction. Now, the Pentium was limited in terms of what adjacent instructions it could decode simultaneously, but it happened enough. It was a common enough occurrence that two instructions could be fetched and decoded simultaneously, and also often enough, two instructions could be issued simultaneously. So what does issue mean? Let me find you a diagram for issue. It's the best one. I don't know.
Yeah. I might get a little bit complicated at that point because I would have no idea how to interpret those diagrams whatsoever.
So I just want to I'm getting a little ahead, but I want to get the concept across. There's this idea of dispatch, which is you fetched and decoded an instruction and you set it up for execution. And then there's issue, which is where you're putting it into execution. Okay. Now, these early CPUs don't decouple those things, right? So dispatch and issue happen simultaneously. So this one's probably way too small. Let's see. Do I have one that's bigger? No, I'm just going to make this thing big. Okay. There. Okay. So if your fetch and decode is figuring out what the instruction is, okay, and then if you've got let's say you've got a processor that can add and multiply, they have separate add and multiply circuits, okay, then you're going to issue an add instruction to the adder or a multiply instruction to the multiplier, and then there's going to be other functional units who do different things, okay, and so in this case the dispatch and issue are the same, okay, so we'll come back to that. So basically, there were kinds of instructions that the Pentium that were independent of each other that would go to different kinds of functional units that the Pentium could issue simultaneously. So an add and a multiply instruction that were independent of each other could start executing at the same time, and the CPU would just keep track of them. Okay. All right. So where do I want to go from here? Okay. Any other notes? Okay. So, now the Pentium Pro, is a big, not the only processor did this, but in terms of Intel processors, another huge milestone in the development of CPUs, because we went from in-order execution to out-of-order execution. Okay. There is a whole other thing that happens simultaneously that I need to talk about in a minute, but I want to get across the idea of what's the deal with in order versus out of order execution. So Is this the slide that I want to talk about? Yeah. Okay, so here we have an execution diagram where we have, here we have an add instruction. Hopefully you can see it. I'm going to add registers 2 and 3 and put a result in 1. And independently, I'm going to multiply registers 5 and 6. I'm going to put the answer in register 4. Okay. And then there's another multiply instruction that's also independent. And then there's another add instruction that's independent. All of these are completely independent of each other. So in theory, all of them could execute completely independently all at the same time if you had enough resources. Okay. But this is a simple in-order CPU. So we're going to run into some resource contention. So this first instruction is going to get fetched, decoded. It's an add. So you're going to send it to the adder. And the next cycle, it can go to the memory stage here, and then the result can be written back. Second instruction is going to be fetched and decoded, and then it's going to spend 3 cycles in the multiplier because the multiplication is complicated. So it's going to take 3 cycles. Now, while that's going on, the third instruction can be fetched and decoded, but then it's blocked. Because you want to maintain program order, you can't send it anywhere. Mm-hmm. So that pipeline stage blocks and can't do anything with this instruction, even though it's fully independent of the multiply.
So the instruction is there. So it's fetched it, but it cannot execute it.
Right. Yeah. Actually, in this case, it's a multiply. So we are waiting on resource content. We're waiting on the multiplier to become free so we can use it here.
Okay.
Okay. Mm-hmm. So that's what now. So here, these gray boxes are the pipeline being blocked on waiting for the multiplier to free up. Mm-hmm. Okay. But then we got another problem. Instruction 4 is an add instruction independent of those. In theory, you could go ahead and put it into execution, but so we can fetch it, but what
are you gonna do with it?
You can't, but this multiply instruction can't leave decode. Mm-hmm. So you can't send this add instruction into decode, so it gets blocked up.
So okay. Three is blocked, 4 is blocked.
Yeah.
Okay.
So yeah, on this cycle, 3 is blocked in decode and 4 is blocked in fetch. Okay. So now, when that first multiply leaves, we can send this I3, the multiply, into execution, and that allows us to send instruction 4 into decode. Okay. And we can send it to add because it can add. You can go ahead and use that resource while the multiplier is busy. You can go ahead and add. Mm-hmm. But now we end up with a problem of having to block because of program order. So in theory, if what would happen is if this instruction were to finish adding, it could go into the mem stage here and then would get written back here out of order. And that would be bad. You don't want to violate program order. Okay. The programmer expects instructions to execute in the order that they wrote them in. Now they don't in modern CPUs. They execute in whatever order, but there's a huge amount of compute resources that are dedicated to putting things back into the original order as far as the external world is concerned. So inside the CPU, it's like a different universe where things are executed in whatever order, but then any impact that the CPU has on anything externally visible, like main memory or IO or whatever, can't be allowed to affect the world out of program order. So there's a part called the reorder buffer that's used for that, but we'll get to that. So, all right. Anyway, so that's the problem that we're running into here. So,
I'm actually getting this. Actually, kind of making some sense. Yeah. When I first looked at this, I'm like, no clue. But actually, the way you're explaining it actually makes sense.
So now, one of the things that's going on in this diagram is instead of the multiplier being a 3-cycle iterative implementation.
So you have 3 cycle on 2, so that's 6. You have to wait for on the multiplier, right? Total.
Well, so the way the multiplier works in this one is you put a multiply in, mm-hmm. and you have to wait 3 cycles to get an answer out.
Yeah, 3 for 1, 3 for 2, so 6 total.
Right, mm-hmm. Right. But you can't overlap 2 multiplications. Mm-hmm. You have to wait for 1 to finish before you can execute the next. Mm-hmm. So what we've done in this one is we've pipelined the multiplier. Okay. So instruction 2 Okay, fetch, decode, send into the stage 1, then stage 2, then stage 3 of the multiplier, and then through the rest of the pipeline. And so now the great benefit here is that for the third instruction, which is a multiply, and it's independent. Okay, there's no data movement from this one to this one. If you can fetch and decode and send it into the multiplier one cycle later.
Yeah. So this wouldn't work if the second instruction was R2 plus R6 plus R4.
Right. Exactly. Yeah, okay. Yes. If this is the result. Yes.
I get it.
See, I'm on the right show here with the right guy. So
I like figuring things out. I mean, that's one thing I like about this show is that, look, we try to conceptualize these things. It's not so much, hey, you can become an instant computer scientist, engineer in a matter of 2 hours, but can you learn enough to say, hey, look, I kind of get the concept to say, look, as long as those are independent, where you have R1, R2, and R3, which are going to take up 3 of the multiplication stage, you can start doing something else. But if they're dependent upon each other, then you can't, obviously, because you have to wait for one to complete for the other. Yeah.
Right.
Yeah, just
right, exactly.
Makes sense.
There's something. Yep. Okay. So, all right. So then
what
we got
the WB. Is that right back?
Right back.
Okay.
Yeah. It stores the result in the register file.
Okay.
So we got, so then we get this add, fetch, decode, add. Okay. But the add only takes one cycle, but because of enforcing program order, we have to wait. It has to block up in the adder and can't get to the write back until the multiplies have cleared. So there's still, not the most efficient thing. Plus, let's see, it couldn't even get in. It'd be in contention for the mem stage anyway. So if it were to try to complete out of order. Okay. What? Oh, that was weird. Okay. Now what we're going to do though is, we're going to change the way the CPU works so that even when there are dependencies, we can still keep fetching instructions and decoding them, and we can keep fetching and decoding even when there's execution busy. Okay. And the reason we're going to do that is because when there are dependencies, we want to be able to run ahead and look elsewhere in the program for instructions that are independent of the ones that are currently keeping it busy. Okay. So what we're going to do is right now, if we want to execute an instruction, the functional unit that we want to execute in has to be free. So if you want to multiply, the multiplier has to be free. Okay. And in this case, we saw that it was pipelined, but the one that wasn't pipelined, you'd have to wait for it to be free. And then all of the input operands would have to be available. So one of the things that we're going to do is we're going to relax constraint 2. We're going to be able to, okay. So let me try to go through this here. Okay. So we have a dependency. And then we have an independent instruction. Okay. So we have a load. We're going to take whatever's in register 2. We're going to add 10 to it. We're going to compute an address from that. And we're going to load whatever's in memory into register 1. Okay. And then we're going to take the result of that and we're going to add 1 and put that result in register 4. But then we also have this multiply that's fully independent. Okay. So for the load, we're going to fetch, decode, we're going to add to compute the address, we're going to fetch data from memory, and we're going to write back. Then we have this add instruction. We're going to fetch and decode, but now we have to wait to issue it because the input is not available, because we're waiting on register 1 to be written. So this instruction has to sit somewhere waiting. Okay. So since this instruction is blocked up in the add stage, then we can go ahead and fetch and decode so okay.
Fetch 3 and
decode.
decode.
Can't issue instruction 2 to add until the load is done.
But you can fetch.
So it has to sit here.
But you can fetch 3 and decode.
Yes, you can fetch 3, but instruction 2 is blocked up in the decode stage until we can go ahead and issue it because we don't have the inputs yet. Okay. So this is blocked up here. We can get instruction 3. All right. So when this one's finally able to issue, we can finally decode instruction 3 and then issue it. Okay. So instruction 2 is going to, add and go through memory and write back, and the multiply is going to finally go. Okay. So the problem that we have here in this diagram is that instruction 2 is in the way of instruction 3. Instruction 3, we could, if you moved instruction 3 earlier, then we could have executed it already or in parallel. Okay. But because of this order, we have to, this instruction is blocking this one.
This might be a dumb question. Why don't they have a second decoder?
Well, so we're going to do something kind of like that. So it's not so much that we're going to have a second decoder, but that we're going to create something that the decoder can dump instructions into that aren't ready to execute.
Oh, and then decode and then bring it back in and carry on. Okay.
Yeah.
So basically, you block, you move it over here, you continue, then you put it back, and then you finish what you had moved. Right. You moved away and then back again. Okay. I'm conceptualizing. Yeah. By the way, somebody got a degree in this, exactly this what we're talking about right now back in the 80s. This is exactly what they worked on. So it's like, so I mean,
he can call me out on all my mistakes.
He's laughing hysterically. Where'd you find this guy? I'm like, no, just kidding. He came to me. No, I've known him. I've known you for a while.
And I barely squeaked through the PhD program,
Most PhD, they all say that too. They're like, oh man, look, I didn't even know what the hell my thesis was about, but I defended it. Right.
Yeah, no, actually I started in artificial intelligence, and my advisor retired, and I wasn't really that good at it anyway. And I'd been a circuit designer. So this guy from UIUC, University of Illinois at Urbana-Champaign, he was hired at Ohio State. And this guy's 5 years younger than me. And I made sure the whole time that I was his advisee that I did not make him uncomfortable about the fact that he was 5 years younger than me. But I went and talked to him, and we hit it off. And it was a great partnership. I was his first advisee, but I already had all this industry experience and stuff and circuit design experience. And I had his undivided attention as an advisee. It was the best decision I ever made. I wouldn't have finished with a PhD if it.
Yeah, artificial intelligence is fascinating, but I think you probably made the right choice.
Well, it was kind of some luck too. Like when I was working as a professor, I didn't have the same luck that my advisor did. I had to work with grad students that did not have the level of education.
Did you have to learn a lot about the physics? I've had Dr. Lachey on my channel, which is Gary Lachey, as I pronounce it, I believe. But he is a solid state chip designer. I mean, he literally is an expert in solid state physics and chip design, and the complexities that he has sent me stuff over the years because I've had him a few times. I'm just in awe. I'm like, this is like God mode level stuff.
When I would teach this course, I would give kind of an overview of fabrication, but mostly with the objective of explaining the economics and yield and some other things like that, just to kind of give people a brief overview. But it really wasn't what I focused on because I was teaching in a computer science department. So, there's a lot of circuity stuff that I could have talked about if I was teaching in like an electrical engineering department, but instead I kind of like kept the focus more towards what software people would want to know.
That makes sense. That makes a lot of sense, actually.
So, but my dissertation, like all that research was focused on dealing with analog related problems, but in a digital way, like at an architectural level. So one of my favorite papers that I published was where I invented a type of forward error correction where the decode was a fairly simple circuit, so that we could take last level caches and lower the voltage to the point that bit stills would start failing. And like we could combine cache lines and use cache lines together to encode the data and be able to recover it despite there being errors in the data. So, but it was being decoded at a digital level. There's like an algorithm that's used to compute what those missing bits are. So yeah, I didn't deal with the device physics problems at a device physics level. I dealt with them at an architectural level. Anyway, so all right. So the fetch and decode are critical resource. We want to get things in and out. Okay. It's like the fast lane, right? We want to keep freeing it up. We don't want anything to ever block up in the decode stage if we can possibly avoid it. Okay. So what we're going to do is we're going to fetch instructions and decode them. We're going to drop them into this table, a buffer. It's a scheduling queue, instruction queue, or reservation stations are common names for this thing. It's basically all the instructions that have been decoded, and you figure out what they need to do are going to be dumped into this one or more of these buffers. Okay. And when their inputs become available, then the instruction queue will detect this and issue the instruction at that time to the appropriate execution resource. But since it's a table that just holds like a bag of instructions, instructions can come out of that issue queue in whatever order they can start in based on the order in which their inputs become available.
They're sequential.
So no, they've been made not sequential.
Okay, non-sequential. Okay, because I remember when I did data, I wrote a program called RSU Unlimited, which program for Radio Shack, my store level. But I wanted a program that would track Radio Shack Unlimited purchases, and so people would buy something. You could put the SKU in, it would give them the address, telephone number, and how to contact them, because we really had no way to really keep track of this stuff. This was, again, way decades ago. So I wrote in Visual Basic a program that would do this using a sequential database that I had actually written earlier in college back in I think it was 93. I first wrote the first database for that. And then I just took this principles of the code. But the way you could write the database, you could have to be either sequential. So the order in, the first thing that goes in is the last out. Rather than more of a dynamic reallocation where you could do more randomization, it's kind of pull wherever. The data files were such that they were sequential. So if you wanted this, you had to get all this out first. So this is similar like that, but that it was non-sequential.
Yeah. So this is basically, so we have to dedicate resources to tracking these instructions so that we can put them back into order when they're done. Yeah. But in the meantime, if you've got an instruction that is later in the program, but its inputs are already available, we want to go ahead and execute that and get it done. Okay. The other thing that we want to do is if you have instructions that are blocked up waiting on their inputs, we want to run ahead in the program and mine for instruction level parallelism. We want to look as far out into the program as we can to try to find more instructions that we can go ahead and execute sooner rather than later while we're waiting on things. So one of the big things that this allows us to do is cache latency eventually got to be a big deal. Okay. So if you want to access memory, let's say it would take 40 cycles to access data from your level 2 cache. Okay. Then, so that you'd have a load instruction that is currently in execution, and anything dependent on that load instruction is going to wait in the instruction queue, not getting anywhere until that load comes back. And then you get a blast of all the dependencies executing, as fast as they could. Okay. So one Sun engineer described these out of order CPUs as races between memory stalls. So you have these memory stalls like last level cache misses where you'd have to wait 1,000 cycles for a data to be fetched from main memory. And so you could run ahead somewhat and fill your instruction window with instructions, and then the CPU just stalls out. And then that load comes back that everything's dependent on. and then you blast through those instructions, so you hit another last level cache miss, and the CPU stalls out. And it's kind of like an ebb and flow of the way these things would behave. So here at the Pentium Pro, the instruction window, the issue queue, could hold 20 instructions. Now, there's also another device called the reorder buffer that we use to put the instructions back into their original program order, and it could hold 40 of those. And there's some reasons why that needs. Yeah. You had a question?
Yeah. So you would have the instruction set, and you're just basically pulling out instructions, doing them if they're not dependent, and then you having something put them back together.
Right.
Okay.
In the original order.
In the original order that they're in. Okay.
Yeah. Mm-hmm. So let's see. Let's go through this one. We have a load. So we're gonna add a constant to R2, and we're gonna load some address, and then we're gonna wait for that, because we got this dependency here. We're gonna add 1, and we're gonna put it into R4. Meanwhile, we had this independent multiply. Okay. So the loads, we're gonna fetch it. We're gonna decode. We're gonna compute the address. We're gonna access the memory, and we're gonna do the write back. Okay. So now here we have the fetch. We're going to decode the add, and then we're going to stash it somewhere. Well, it's going into the instruction queue, but in this diagram, we're just, marking it. Okay. So it's waiting it's been dispatched, but it isn't issued yet because it doesn't have its inputs. So, but because it's been moved out of the decode stage, decode is now freed up, so we can fetch the multiply and decode it and send it to the multiplier. Okay. And it can go and start executing the multiply in parallel. Mm-hmm. Okay. So meanwhile, while this multiply is going on, the load finishes. We have the input to the add, so we can issue the add, and then it can fall out of the pipeline.
So L2, we're circled at L2. That's being sent to some buffer. That's keeping it. That frees up the FU. Now L3 can be issued. Right. You don't need it. But you don't really need. Why do you need to free up the FU?
We're freeing up the decode.
You free up the decode. Okay.
You're freeing up the
decode. Yeah. Then you're sending the FU to the buffer. Now it allows you the multiplier FU to work.
Right. Okay. Yeah. So this one, it's not really in add. It's in the issue queue.
Yeah. Okay. I got you.
It's been moved out of decode. Yeah.
Mm-hmm. But it frees up the decoding thing. I got you. Yeah.
Yep. Right. So this one took 11 cycles, and now it takes 9. So
this is cool as hell, man. I'm telling you, I'm nerding the hell out. This is like, seriously, if I had even conceptualized this crap back in the freaking 70s and 80s, I'd probably be far more computer literate than I am. Because I have a basic understanding like anybody else of stuff. Most of us have been around for a very long time with computers, but nobody besides maybe you and Hal Lando out there, would have ever known this stuff back, when we were like 12 or something, Oh, so this is magic to me. This is great. I love this. I really do.
So we were talking about having to put things back in program order. Okay. Mm-hmm. So these instructions are going to execute in whatever order, but they're going to, but what we don't want is to violate the sequential execution model, which mm-hmm. is this programmer expectation that everything's going to execute in the original program order. So there's something called a reorder buffer. Okay. So we're modeling it. It's not physically circular, but we're modeling it as a circular queue. Mm-hmm. And so the way a queue works is you put stuff into the tail and you pull stuff out of the head. Okay. So every time an instruction is decoded, we're going to put that instruction at the tail and advance the tail pointer. Okay. And so the head of the queue is the oldest instruction that is not done. Okay. And the tail of the queue is the newest instruction that's been put in there. So the states, these instructions, there's unused, like, we haven't fully filled the reorder buffer. Mm-hmm. And we have instructions that are in an execute state. We have instructions that are in a completion state. And I don't remember what W is, probably writing back or something. Okay. But what matters is that we have instructions that are in the completion state. So they have executed, they have handed off their result to any dependent instructions that are in the issue queue. Okay. But they can't be retired yet. We can't remove them from the CPU. We can't make their effects permanent because there are instructions earlier that are still busy executing. Okay, so we're gonna so this is the component that tracks the instructions that are executing out of order and puts them back into the original program order. So every time the state changes of an instruction, then its entry is going to be updated. And when it goes from the execute state to being completed, then it can be retired and we can pop it out of the queue. Okay. So if an example would be if we're going to write to memory, can't write to memory out of order because that's an externally visible thing. Mm-hmm. Okay. You can read memory out of order, but you can't write it out of order. So, so if there's a memory that's to be written, then it's going to be stored in the reorder buffer. And then when the instruction retires, that's when it's going to actually get sent out to the cache hierarchy. Okay. And so you can see that we've got all these instructions that are, have been executed out of order, but they got to sit there and wait because we have to put them back into order. Mm-hmm. So executing
first in, first out. There we go.
Yeah. Mm-hmm. Yeah. This is a FIFO, mm-hmm. Right? Okay. Let's see.
Just to let you know, we're probably gonna have to wrap it up a little bit. We're gonna have to have part 2. There's no question about it. No part. I mean, this is so much to cover.
I can go longer if you can.
I can't. That's actually
up to
tonight.
You. Okay, that's fine.
I can't. I got something to do.
All right. Okay. All right.
Not too much longer, at least. But so if we want to get a good kind of a point to maybe table it, and I will schedule a part 2 because I love this stuff. This is fascinating. So
I'm just going to mention one thing that's kind of independent of all this, maybe just so we're done with the Pentiums. Okay. Mm-hmm. One of the other advancements is the CISC architecture. So the instruction set for the Pentium is for the x86 processors is really complicated. Okay. So one of the things they did to get more performance out of these things is instead of fetch, decode, and all this stuff, they had this translation front end that the first several stages of the CPU pipeline, what they do is they translate the complex instruction set, x86 instruction set, into an internal instruction set they call micro-ops. That's more like a RISC processor. And those are what get scheduled and executed. And so it's like everything's in French. But before I can do anything with it, I have to translate it to English first, and then I can do all my stuff, and I can get the job done, right? And under the metaphor that somehow English is simpler than French, which isn't true, but whatever. So that was a big deal because those micro ops are easier to schedule, and you can take a complex instruction that does multiple things and break it up into smaller steps and schedule them independently. So that was a big improvement in performance there. Okay, so that I think might be a good place to stop.
Go back to that. Go back to the spreadsheet real quick, just for a second.
Okay.
Okay, so go all the way to the So where are we at now? And real quick, I just show what we'll touch on next time. But where are we at in 2022?
Okay, so one of the last things that I was going to talk about is the Apple M1. See, there's so much I want to build up to be able to talk about the M1 because it is an absolute beast of a CPU. Okay, where x86 processors have gotten to the point where they can fetch they can fetch 6 instructions at once. And they can issue maybe 12, but they can only decode and fetch 6 at a time. The M1 can fetch and decode 8.
And it's 5 nanometer? And what is that? So when it says 2 plus 4, is that 2 physical cores, 4 logical cores?
No, 2 low power two high performance cores, 4 low power cores.
Oh, okay. Because usually when I see 2 plus 4, it's usually you have 2 physical cores and you have like 4 logical cores. But these are how do they get down to 5 nanometer? That seems like magic because
ultraviolet.
Because when I remember, again, things changed obviously, but I remember there was like literally a physics cutoff of something like a 6 or 8 nanometer that you couldn't even physically go beyond that because of quantum mechanical tunneling effects. So they have developed now ways of kind of like getting around that. Because 5 million,
Well, okay,
5
so
nanometer is small.
transistor technology has advanced substantially. So they're using ultraviolet lithography so that you can, get smaller. But now you're on, you're getting on the atomic scale. But there's some other weird stuff that they did, like with the FinFETs at the 22 nanometer. What Intel did was, instead of the gate being on top of the conduction channel, they etched it so that they could wrap the gate around the conduction channel. And then they've got this thing where they've got I have to go find a diagram, but they've redesigned the transistors so that there's like multiple gates on them or something. I don't know. They've done some weird stuff where they wrapped the gate around three-dimensionally around the conduction channel. Yeah. So, because one of the things that happened at 32 nanometer, if your CPU was on but not doing anything, it was using about 40% as much power as when it was at full bore.
Mm-hmm.
And so at 22 nanometer with the FinFETs, they were able to reduce that leakage current. So basically wasted power substantially, because basically transistors weren't switching off completely. Mm-hmm. So they've been working out ways of improving the degree to which they're limiting the quantum tunneling through these transistors.
That's awesome.
So yeah. So this processor, so you look at the instruction window. Back in the Pentium days, you could run ahead 20 instructions, okay? And they've been steadily increasing the number of instructions that these processors could hold on to. The latest x86 processors, they have a reorder buffer of 512, but that's not the size of the instruction window, whereas the M1 has a full instruction window of 630 instructions. So you can run ahead, you can unroll loops dynamically and all kinds of stuff. You can run hundreds of instructions ahead of what's actually executing. The L1 caches have been, stabilized at about 32K just because of the speed. You want a certain speed of the L1 cache. Okay. Somehow Apple have managed to substantially increase the size of the L1 caches. Okay. And they've got a 12 meg last level cache. And so they have, and then they've also have put the main memory in the same package as the CPU. So the latency to main memory is substantially faster. So they're able to decode more instructions. They're able to issue more instructions simultaneously. And so this processor that is executing a completely different instruction set from x86 is able to outperform x86. Apple's just like, getting ready to wipe the floor.
Apple's always, they've had some amazing stuff. So this is a chipset that, what's this, before we end this, what computer system would that be in yet?
MacBook Pro.
MacBook Pro.
Yeah, the latest MacBook Pros. It's been out since 2020. Mm-hmm. Like my MacBook Pros are just old enough that they don't have it, but my wife has a MacBook Air that has the M1 in it. You would never know, because you can run x86 code through a dynamic translator. Mm-hmm. So any old applications will still run it.
So it's that's awesome. I mean, it's backwards compatible to that kind of architecture.
And and substantially lower power. This thing about using a simpler instruction set, so you don't need this micro-op decoding front end, basically the CPUs to do the same job are simpler because the instruction set architecture is simpler.
So you could run Windows on this, even though it's not for Windows PC. You could easily run Windows on it, I would assume.
There's, I believe, an ARM version of Windows that will run on it.
Yeah. All right, we got to wrap this up, Tim. This has been amazing. Again, this brings me back to old school days of the Hercules monitor and green screen monitor, and you're typing on those XT computers and we hear the clickety clack clack, and that's when you actually felt like this is a computer. This is like something that is beyond human intellect to even develop, and going back to like the 70s, 80s to where we are now, I don't think people really appreciate the leaps and jumps in technology that have occurred, each step by step that you were showing to get where we are now. We've lived it. We've seen it. I remember when the Pentium came out. I remember when they had a floating point bug, and I remember they're like, I was one of those guys that said, "Hell, what the hell? I never need a Pentium for, right?" Yeah, almost like a Bill Gates thing. But I quickly, I realized after I was thinking that, I was like, no, of course, we're going to need Pentium, Pentium 2, whatever. But yeah, so there's a lot of people that actually enjoyed this a lot that have backgrounds in computers. And so I think that this particular episode is more catered to them. This was more niche, no question about it. It wasn't meant to be a dumpster fire. It wasn't meant to be controversial. It wasn't meant to be anything but informative. And I think that you've done that exceptionally well. And I appreciate it.
Yeah.
So
well, it's quite an honor for me to be on the show. I've watched a lot of your shows going back years. I haven't been keeping up lately, but
that's probably a good thing. That's probably a good thing. That's probably a good thing, to be honest with you, because the effery is real, to say the least. It's well,
I changed jobs. I changed jobs in November, so I've been pretty busy. Oh,
don't worry, you'll be lambasted like they always do. Don't worry, you'll have your share. But anyways, no, we'll get a part two. We'll get a part two. I don't know, April or something. I'm pretty booked for April, but I might have an opening. But I'm booking for May right now. But we have some great things coming up. But I do want to thank you for that. So, where can people find you?
Thank
and
you.
I can put your information in the video description, so they can find. I know I find you on Twitter. But is there anything anywhere else they can find you?
What I could do is I've got a Discord. It's Minecraft related, but I could put the invite in there.
Yeah, actually, that would be great.
Yeah, I'll tweet you the Discord invite,
and I will get that in the video description ASAP.
Cool. Yeah. Well, it was a great honor for me to be on the NonSequitur Show.
I appreciate that. You know what? And I'm gonna say it. I want people to think of it as something that is special. We've had a lot of great guests on this channel for years. Hopefully, like I said, I'm at least going to be going to March, April, May. Hopefully longer. I mean, it always depends on what I want to do, but right now I'm booked and I'm enjoying it, and that's what it's going to be. And people want to follow, people want to subscribe, people want to support the channel, they want to become members. That's all up to them. If 5 people watch or 4,000 people watch, what it is somebody's going to get something out of it, even if it's just us, the people that are doing the show. So anyways, Tim, thank you very much for joining us. The rest of you guys, see you guys later. Peace.
All right.